It used to be more of a makeshift place. It's wonderful how it's expanded. It's much fancier. So I want to thank the organizers for putting this very stimulating workshop together and allowed me to participate. So what I want to do is I want to tell you, in the spirit of deviating just from liquid crystals, I want to tell you about something quite wild, and at least part of it will not be directly related to the main theme of the workshop, but I hope to make it relevant by sort of a connection to something that's quite familiar to most of you, namely elasticity. And so this is the work that was done with a very talented postdoc in Boulder, Michael Pretko. And what we've done is we've established a connection between something that's quite exotic that's been explored in the last 10 years in quantum many-body theory and quantum spin models of magnetism, very exotic models. We, in a sense, were able to demystify these exotic phases of matter called fractons, which I'll explain, and demonstrated that they're actually basically rigorously demonstrated that they're related to elasticity, something very familiar to all of us. And so it provides this duality, or this connection provides a very nice interpretation on one hand. Well, it's kind of a symbiotic relation between both of these. We can maybe think about new types of elasticities, having understood some things about these fracton states of matter. And on the other hand, it allows us to think about and predict new types of fracton states of matter from understanding, from much of our understanding of elasticity. So I tend to ramble on, and so I always run out of time. So let me just, when you walk away from this talk, if I don't finish, you hear the punchline. So it turns out, although there are more than one type of a description of these states of matter, it turns out there are these states of matter called fracton states of matter, which can be at long wavelength and low energies, they can be described by a funny kind of electromagnetism. So there's an electric field. It turns out that electric field is a tensor rather than a vector that we're used to. So it's a symmetric tensor, a rank 2 tensor. There's a magnetic field, which is a vector. And there are charges and a Coulomb's law. The Coulomb's, or Gauss's law. Gauss's law is generalized. It's not just the divergence of E. You can sort of guess this. If you have a vector, then you have just one index to create a scalar charge. Here you have a double divergence on both indices. If that double divergence is non-zero, you get charges in your system, just like by analogy with ordinary electromagnetism. Those particles are called fractons. Then you can make dipoles of those charges. Plus or minus fracton is a dipole. So that's a description of some funny states of matter, which I'm not going to bore you with, although I'll spend some time talking about it, but I'm not going to get into details. What's amazing is, and that's what this duality establishes, is that this really mysterious state of matter, which up until this point has not had any realization, has direct connection, really mathematical connection to something that's very familiar. So this electric field, the stencil electric fields, ends up being mapping onto just a strain tensor. Magnetic field, vector magnetic field is just a momentum, lattice momentum. So the gauge modes map onto phonons. Fractons map onto disclinations, defects, and dipoles map onto dipoles of disclinations, namely dislocations. So that's it. That's the message. I can really just stop here. The rest you can just read the details of it, but since I have another half hour or so, I will proceed. So, I'll, with that introduction, so you can find the details in this paper. I'll tell you about new types of topological quantum liquids called fractons and build up to that. Then I'll talk about these higher rank gauge theories that describe these states of matter. Then I'll remind you about elasticity, briefly show you how this duality is established, and then finish with further directions. So feel free to interrupt. Yeah, Robert, that was an invitation to you. Yeah. This has nothing to do with that. Let me proceed. Sometimes there's degeneracy in names. It was named for a strange reason that maybe I'll mention when I get to that point. So much of our understanding of states of conventional matter includes these ingredients. So we typically, if you want to have some states of matter, we understand states of matter as some kind of a spontaneous breaking of symmetry. Translational symmetry, rotational symmetry, some internal symmetry like in superfluids, or spatial symmetries like in liquid crystals. So what does that mean? Well, as Landau taught us, that means we usually have some local order parameter that tells us locally that the system describes whether the state is an ordered state, you're in that state or not. Then once you have that, you can talk about topological defects and many other things that have already been mentioned. So then we classify states of matter as by broken symmetry. And okay, for the if this was a quantum workshop, I would say these are, in quantum context, these are called short-range entangled. They're not very interesting from the point of view of quantum entanglement. And so once we have this local order parameter, we construct a Landau functional, and so we have a Landau theory description of it. And then if they're often, not always, there are fluctuations that become important, so then you have to do not just minimize, but do statistical mechanics over this order parameter. So that's conventional. All of conventional states of matter are understood in this way. But it turns out there are states of matter which cannot be understood in terms of this local order parameter. These go under a variety of names. One can call them topological states of matter, although that's not an ideal term because some of them don't have a kind of a topological, well-defined topological description in the sense that they're gapless. Usually topology is used in the context where matter is gapped, so then you have a good notion of topology. There are no gapless modes. But it turns out that there are some states of matter that cannot be characterized by a local order parameter. So these have been known for ages. Go back to Anderson, and there's here some of the characters that have been involved in studying these over the years. So I call these conventional quantum liquid states of matter. But really, probably maybe for this audience, maybe the simplest phase of matter that's topological, that doesn't have an order parameter, is a Kosterlitz-Thouless phase of a two-dimensional, let's say, XY model, or two-dimensional crystals. If you ask what is the order parameter, let's say for a crystal, which is the rho g, the Fourier component and some reciprocal lattice vector of the density, on average that's 0 because in 2 dimensions fluctuations of finite temperature vanish. But nevertheless, there's an ordered state, and that ordered state is distinct from the disordered phase. Both phases, both ordered and disordered phases of a 2D XY model have vanishing order parameter, the Landau order parameter, but nevertheless they're distinct, and they're distinguished by topological defects. In one case, topological defects are confined logarithmically. In the other case, it's a free plasma with just short-range interactions. It screens. So that's what I mean by a phase of matter doesn't have local order parameter, cannot be described by a Landau theory. But there are other ones, and without getting into too much detail, they occur often in frustrated systems. Actually, some of them we heard about in these floppy modes of a solid that is quite closely related to some of these states, magnetic states of matter. But probably maybe the simplest one you can think about for this audience is if you think about quantum Hall effect, if you take two-dimensional electron gas, apply a perpendicular magnetic field, strong perpendicular magnetic field, that you have Landau levels. Well, if you fill those Landau levels, you get a liquid, and that liquid is a featureless liquid. If you have a Landau level, nth Landau level filled, for every Landau level that's filled, you have a liquid. Those liquids seem to be locally look the same. They're gapped, liquids of electron matter, two-dimensional electron matter, but nevertheless, they're distinct. There's no local order parameter. You can't really distinguish them locally. They just have some density. There's nothing different about them locally, but globally, they're distinct in the sense of you can measure, for example, Hall conductivity and discover that, at different filling fractions, whether integer or fractional, you have different properties, different Hall conductivity. So it's a very strange thing where much of the focus in the subject has focused on, has turned to understanding disordered phases of matter, which are nevertheless disordered in a different way. You have two liquids and liquids, and they're all distinct, but when you look at them locally, there's nothing distinguishing about them in the locally. So those are the what I call conventional quantum liquids. And by liquids, I don't really mean liquids just in the sense of that they flow. Liquids, I mean by, I use it synonymously, that's why it's in quotes, as a disordered state of matter. It has no local order parameter. And nevertheless, there's some underlying order which is more subtle than just local order parameter. So they have all kinds of funny things. First of all, so they often occur like in fractional quantum Hall effect, where you have fractional quasi-particles, charged quasi-particles, fractional statistics. They occur in these funny Pyroclo lattices, which are called spin ice, or on Kagame lattices, magnets on Kagame lattices, where you overturn one spin and you get two excitations, which you can then pull apart, and they have fractional charge or fractional spin charge. So there's various models that exhibit these. Often these excitations in these models are described by fluctuating strings, and the particles are the ends of those strings. So the fluctuations are these strings, and the particles are at the end of those. So this would be like a string of electric field terminated at electrical charges. So electrical charges are connected by a string. So not surprisingly, given that the description in terms of strings, charges connected by strings, often you can find a gauge field description, sort of fake electromagnetism, a pseudo-electromagnetism that describes modes of these theories. So again, I'm sorry if I'm not. It's not probably not appropriate to get into too many details. This is just sort of as a background to give you some flavor of still conventional, non-fracton quantum liquids. So again, so they have a gauge theory description, like a U1, like magnetism. So let me give you an example of this. So there's these frustrated materials called spin ice, after conventional ice, where for some energetic reasons, okay, so for example, so where spins live on the so-called Pyroclo lattice, this Pyroclo lattice can be thought of, is a lattice constructed, is built by corner share tetrahedra. So this is a three-dimensional analog of the Kagame lattice that you saw in the previous few talks back. And there's a rule, what's called ice rule, that every tetrahedron, there are 4 spins on the tetrahedron, and one spin is shared between 2 tetrahedra. And the ice rule is there should be 2 in, 2 out rule. So their total number of net number of spins out pointing out should be 0. Okay, so here the rule is obeyed. But then if you overturn the spin, now you create 2 charges. A positive charge where there's more spins coming out. Think of that as flux, electric flux coming out of that electric charge, positive electric charge. And here there's 3 errors coming in and 1 coming out. So this is like a electric negative charge. And they're connected by a string. The beautiful thing is inside quantum state, ground state, the line tension of this string actually vanishes. So you can think of it as like a Bose condensation of these strings. And this is sort of a point of view that was advocated long ago by Wen. And so when you have condensation of these strings, then line tension vanishes. And so then these particles are no longer confined by a string energy per unit of length. And so then what emerges out of this microscopic lattice model is actually magnetism, effective pseudomagnetism, very much like our electromagnetism in our world, where electric field lines, particles are these charges, like I indicated here, but they're no longer confined by strings. They have just Coulomb energy. So this is called the Coulomb phase of this kind of a magnet, and it has very exotic properties, beautiful properties. Okay, so this is just give you some flavor of how out of something microscopic like this with some constraints, local constraints, what emerges at long scales and low energies is something that looks like electromagnetism, where the electromagnetic fields are, for example, electric fields are these lines, fluctuating lines. And because you lose energy per unit of length, the tension vanishes, charges are no longer confined. It's not screened. It's so these charges are not dynamical charges. So I'm putting in, it's just pure electromagnetic. I can also condense the charges, for example, and then I would have a Higgs phase, which would screen the electromagnetism and make it gapped. I would gap out the photon. But just think of it. Don't think of the ground state of this magnet as having no charges. And so if I want to describe that ground state, it's a superposition of all possible configurations of these lines, electric field lines. That's how you can think of it. And it's a superposition because it's a quantum state of matter, so E and B don't commute, and so then it's a superposition of all possible line configurations. Now, I could go in and flip two spins. I could flip a spin, and now, if I wasn't in that ground state, there would be line tensions. I couldn't separate them too far. But because I'm in this funny, this exotic phase, now I can separate these two charges, and those two test charges that I created will have a Coulomb interaction between them. Okay, so this gives you some flavor. So now there's even more exotic, even more difficult phases to wrap your head around. I'm not going to bore you with it too much details about these microscopic models, but there's some kind of a spin half models on a lattice which involve multi-spin interaction. Okay, and they were first discovered in kind of a recent reincarnation by Ha, who was thinking about sort of quantum memory and quantum computers. This guy is a quantum information person at Caltech. As a PhD student, he discovered these models, and he called them fractons. And that's because when you flip a single spin degree of freedom, you generate excitations that live in a fractal. And so he called them fractons. And so this is the fractal operator that Ha invented or discovered. Now there's much simpler models that, again, I'm not going to spend time describing. So when I first heard about this 2 years ago, I kind of thought, well, this is so complicated. At that point, there was only these Haas code that existed, so I kind of thought, well, this is let me not waste my time. These are some totally unphysical, microscopically unphysical models, so there's no really point trying to delve into these microscopic models of Ha to try to understand them. Since then, actually, these models are still unrealistic, but a lot easier to understand. But luckily, I kept thinking about these systems, and rather than focusing on what the actual model is, details in the model, I kind of focused on what are the consequences of this, of these models. What is kind of the general property that comes out of these models? And the general property is that unites these models is they exhibit excitations that have very interesting properties, and those are the excitations I mentioned already, fractons. So fractons, these excitations that you generate when you flip a spin, are immobile. In isolation, a single fracton, it's a localized object. It's a particle, costs finite energy to create, but it cannot move. So I can create it here, I can create it here, I can create it here. Those states are degenerate. But there's no local way to hop one fracton from one lattice site to the next site. So it's completely immobile. There's no local there's no local move, no local Hamiltonian that can move a particle. And for me to really explain it, I have to get into these models. I don't want to do that. I'll have another way of understanding it in terms of these gauge theories, so then you guys will all be happy. We don't need to understand it in terms of these lattice models. That's what's the appeal of that gauge theory. So fractons are immobile. That's one ingredient that I noticed. The second ingredient is dipoles of these fractons, at least in some models, are subdimensional. They can only move perpendicular to the dipole vector. They cannot move along the dipole vector. So that's kind of cool. So amazingly, I kept thinking about it, even though I didn't really understand this Ha code. It was just way too complicated for my brain. But I realized I've heard about something like this before. So I started thinking about crystals and defects in those crystals. So the natural defect in the crystal you can think about is disclination, as has been already discussed. And it's a fact that I actually didn't appreciate at that point. Originally didn't appreciate it, but as I thought more and more about it, I realized it's true. And maybe some of you were aware of this. disclinations in a crystal, if you actually think about it, are immobile. You can't move a disclination. It's kind of strange. Like you can put a disclination, you can create this kind of a cut and reglue it, and you could do it anywhere. You could cut this a little further, and so you think it's mobile, and I've never thought about it, that it's actually immobile. And one way I can argue that it's, so if you try to move it, you're going to rip the piece of paper if you try to move the point of that cone on the piece of paper. And so one way to think of it is, the way I think of it is, you can think of a disclination as a ray, infinite array of dislocations. So if I want to move that end, which is a disclination, one lattice side further, then what I need to do is I need to add another dislocation. But adding another dislocation is a non-local operation. In terms of a defect, it looks like I'm just moving a point. But think about it like a local Hamiltonian where I just hop atoms around. I can't move, adding a dislocation is like adding an infinite array of atoms. So that's not a local operation. It would never appear in any physical Hamiltonian. So disclination is immobile. Furthermore, this is a more familiar fact. Dislocations are mobile, but they can only move. They cannot climb. And in order for them to climb, they need to eat up. By conservation of atoms, they need to add up atoms, or they need vacancies or interstitials to climb. But they can easily glide. So in the absence of vacancy interstitials, which at finite temperature you always have, but at zero temperature, if you think about quantum ground states, you don't have, you may not have, then in the absence of vacancy interstitials, you can only glide, you cannot climb. So that's immediately very tantalizing, although at this point, very just kind of an idea, loose connection to these Fracton models. So anyway, right away, so I was at KITP, I was thinking about this, couldn't stop thinking about it. So I wrote down sort of a classical duality. So you start out with elasticity theory, no dynamics here. And it turns out you can dualize it, which means you can describe it in terms of these topological defects. And what you get is this dual Airy function, or I forgot the name of it. There's another name for it. You can describe it in terms of a potential phi, which solves the stress-free condition. And what you get is you get a funny kind of a elasticity, which is a Laplacian elasticity of that stress function, coupled to charges. S are disclinations, and curl of B is a dislocation, and its curl also contributes to disclination density. So this actually is a nice way to capture this physics. If you have a bunch of dislocations, in the end, you have a non-zero curl of dislocation vector. And so that's disclination comes in as this non-trivial curl. So you have this duality. Yep. This is in 2D. I'm focusing on 2D. I don't know how. You can generalize it to 3D, but it's quite a bit more complicated. Right, so I imagine I put a test charge in. Of course, I can put those interactions in, and I do. I will put it in. Okay, if I want to describe a phase of matter where I have a lot of these defects, then I need interactions. But if I just want to describe the state where they don't want to be, and I just put them in as test charges, it's very related to the earlier question, then I don't need the interactions. Think of it as a vacuum of them. Okay, anyway, so that was just a tantalizing idea. There was this duality, kind of classical duality, or a static duality, but I wanted to think about it further, but there was a kind of a stumbling block. There was a lot of description of these Fracton models, which again, I'm not going to bore you with, but there was one particular description which I already alluded to in the beginning, in terms of higher rank tensor gauge theories, this funny magnetism that I described earlier, which has these tensor gauge electric fields, which double divergence replaces the Gauss's law. And this tensor gauge theory has existed before, but Michael Pretko, as a graduate student at MIT with Senthil, looking at these gauge theories, realized that they actually capture some of this Fracton phenomena. And I want to explain to you how it does that. So again, these tensor gauge theories existed before, but so let me explain to you how, in terms of these much simpler formulation of fractons, you can understand this immobility of charges. Okay, it's really very beautiful. And the way you understand it is this. In these tensor gauge theories, because of the double divergence of the tensor electric field, being, let's say, 0 in the vacuum, you don't just have conservation of charges, you also have conservation of dipoles. So you cannot change dipole density. Not only can you not change charge density, you cannot change dipole density locally. And that immediately leads to Fracton phenomenology. It means if dipoles are conserved, charges cannot move. And that's very easy to see in terms of even cartoons. So imagine, basically the bottom line is, if you want to move charges, moving charges generates a dipole. And that's forbidden by dipole conservation. So the way you see that is, imagine I have this fracton here and I want to move it. So normally in ordinary magnetism, I just move it. But here, to move it, its motion corresponds to creating a plus or minus dipole to cancel this change. So if dipoles are conserved, I don't have this dipole, I cannot create it. And in tensor gauge theories, these dipoles are conserved, so I cannot move a charge. But dipoles can move because the quadrupoles are not constrained. So what you get is, okay, so what are these tensor gauge theories? They look like this. They look like ordinary magnetism. E squared plus B squared. It's just E and B are funny tensors and vectors. And they have in quantum mechanics, they would have non-trivial commutation relation. So E is canonically conjugate to A. So think of E as the momentum and think of theta as the position. Or think of it as like for bosons, this is like the charge density, and this is like the phase, and they're canonically conjugate. And magnetic field is just the curl of the electric field, funny curl. So now you have Gauss's law, which I already mentioned. Gauge freedom looks like this. Rather than changing A by a gradient of alpha, it's a double gradient of alpha. There's 2 gapless gauge modes. And for this scalar charge theory, there's a linear dispersion relation. So here's how this conservation principle comes out. So if you have this double divergence electric field, there's a hidden conservation law. Of course, charge is conserved. So if you integrate charge over all 2-dimensional space, then you can replace rho by divergence, and therefore it integrates. That divergence allows you to integrate to the boundary. That means the only way you can change charge is by bringing it through the boundary. So you need current to bring that in, and that's why charge is conserved in some region. But in addition, because this is a double derivative, in ordinary magnetism, that's all you have. But because this is a double divergence, even rho times x is also conserved. Because now I replace rho by double derivative and do integrate by parts, and I can now integrate that to the boundary, and that's still conserved. The only way to change that is to bring flux in through the boundary. And so that's how these gauge theories, this simple double divergence Gauss's law generalization, which comes from the fact that it's a tensor theory, accounts for dipole conservation, and therefore immediately by implication immobility of particles, of charges. So now let me switch gears and talk about elasticity. Yes? Yeah, you can. Yeah, there's a second derivative. It's very much like, you can think of E as fundamental, and you can think of the E and A are canonically conjugate, very much like momentum and position for harmonic oscillator. There's a scalar potential, there's also vector potential, just like, I'll write it down in a second, but just like for ordinary electromagnetism, there's a electric field's a gradient of a potential, scalar potential. Here, electric field, which has 2 indices, is a double gradient of a scalar potential plus a time derivative of the tensor vector potential. So it's very, very much extends. Similarly, so elasticity, I don't have to dwell on this for this audience. There's a displacement U, U is the phonon, there's a strain tensor to linear order, looks like this. Hamiltonian is momentum squared plus elasticity squared. So it looks like this for, let's say, isotropic crystal. There are topological defects. There are dislocations, which is a non-trivial curl of the bond angle, and the bond angle you can relate to the strain as the antisymmetric part of the non-symmetrized strain. So this is really different than that. This is non-symmetrized. So, okay, dislocations is a non-trivial curl of the gradient of the displacement, described by a Burgers vector. And then there are vacancies interstitials. So now let me talk about, before I turn to this Fracton-Elasticity duality, let me just remind you about dualities more generally and specifically the simplest duality that we know about that goes back to Dasgupta and Halper and Fisher-Lee and Peskin, and there are a couple other works before that, but these are sort of the clearest formulations of it or demonstrations of it. So in a superfluid or an XY model for this audience, you have some kind of a Goldstone mode phi of the or angle of the XY model, and the way you describe vortices is as a non-trivial gradient of a curl of a gradient of that phase field phi. And that gives you the topological charge rho, or density of vortices. It turns out you can perform this duality and think of it in a complementary way. You can think of this fairly conventional state, superfluid state, or XY state of a XY model, 2D XY model, as just all you do is rotate the gradient of phi by 90 degrees with this epsilon symbol. So define a electric field which is perpendicular to the gradient of phi. So here you see it's azimuthal, pointing azimuthally. So now the perpendicular gradient will point radially, associated with the electric field. So this non-trivial curl of a gradient just looks like a divergence of that electric field. And so you can map these vortices onto charges. And amazingly, if you look at the Hamiltonian, you have a gradient of phi squared plus the density squared. So in the quantum model, these are canonically conjugate. So I have to include them both. So this is just XY model, quantum XY model. So the Goldstone mode is phi, and n is canonically conjugate. So then you literally can just think of this as the electric field, and this is the magnetic field squared. So this just becomes E squared plus B squared. And in that description, an insulating phase, non-superfluid phase of this XY model of these bosons is a Mott insulator, and that maps onto a condensate, a superconductor of vortices. So when these vortices condense, you end up getting a Higgs phase, which describes this Mott insulator. Okay, so what we want to do is we want to just mimic this duality, but just phi is no longer a scalar. Phi is now going to be a displacement field, this phonon u. It's really just, after you think about this and realize the connection, mathematically it's just a trivial generalization of this. So you start out with a Lagrangian, which is elastic energy, uij squared, plus 1/2 mv squared. And you introduce stress. Think of it as a Hubbard-Schrödinger field. It's just another way to write the Lagrangian. Momentum squared, stress squared, and then stress couples to the gradient of the phonon, and momentum couples to u dot, to the velocity. That's the usual Lagrangian of elasticity, if you wish. You don't have to think of it as quantum, just think about it. I'm trying to include dynamics as well. So then, disclinations are just a non-trivial curl of a gradient of, you can show that this is just a disclinicity. So double derivative with these epsilon symbols like this of the strain tensor is the disclination density. Now, if you take this Lagrangian and write down its Newton's equation, write down its Euler-Lagrange equation, it's just a momentum conservation. Pi dot equals to divergence of stress. Well, amazingly, let's define a magnetic field, pseudo-magnetic field, which is a rotated 90-degree rotation of this momentum. And let's define an electric field, which is a funny rotation of the stress. If I do that, then this Newton's equation just becomes Faraday's law. D pi dt becomes dB dt, and what used to be a divergence of stress becomes a curl of electric field. Okay? So it just allows me to make this connection, and then the gauge fields are, magnetic fields and the electric fields are related to these gauge fields, AI and AIJ, and there's a gauge freedom that I mentioned earlier. And so this is the electric field that you were asking me about, how it's related to the potentials. Okay, so Newton's Lagrangian here can be rewritten as electromagnetism, where the identifying features, Newton's law becomes Faraday's law in this new description. Very much like when I was doing this for here, the currents, which are the gradients of phi, or stresses, became electric fields, and densities were the magnetic fields. Okay, so to summarize, this is the summary of it. The The Lagrangian that I wrote here, you can almost read it off here. If you squint your eyes and don't distinguish between uij and sigma ij, it's already here. You see, time derivative of u is kind of like the momentum. So that's like the magnetic field, b squared. This term, kinetic energy, is like the b squared. And the potential energy is like the e squared, where c is just some redefinition of this elastic constant tensor. So you have v squared plus u squared. That's the same thing as b squared plus e squared. And then these potentials from which these e and b are made coupled to disclination density and disclination current. Yeah? Which one? Here? It is, except this is a tensor. There's an extra index. It's eij. Yeah, I mean, the structure of it, look, you write down the simplest theory. Simplest theory is going to have, it's always harmonic oscillators. The only thing we know how to do is harmonic oscillators. So it's just p squared plus q squared. Right? So fracton charges are the disclination densities. This current jij is actually a current which has two indices, and its physical microscopic interpretation is the cross product between the Burger's vector and the velocity of that Burger's vector. So that's actually quite beautiful. So Gauss's law is this, and the Ampere's law looks like this. Time derivative of E is the curl of B equals to the current, and the current is this guy. Well, this current, this is something that Cristina Marchetti and I discovered in 1998, thinking about melting of vortex lattices and thinking about hexatic phase of vortex lattices. We discovered this relation. We were thinking about vacancies interstitials and their motion. If you think about dynamic continuity equation for vacancies interstitials in a crystal, in the presence of dislocations, you discover that they're not conserved, not surprising, because dislocations can create vacancy interstitials. And the way they're not conserved is they have a right-hand side, which is a trace of this current J. And if you think about what the trace of this current J is, it's nothing more than the V cross B, where V is the velocity and B is the Burger's vector. So what this current says is, what this equation says is, if I have a motion velocity, if I have a velocity of a Burger's vector, of a dislocation, that's perpendicular to the Burger's vector, which means a climb, I'll create vacancies interstitials. I'll have to create either vacancies interstitials, depending which way it moves. So here, this comes out from this gauge theory. Okay, so that's just a sort of that picture summarizing this. Okay, so with this duality, you can then see now this familiar picture where, which summarizes everything I've said so far. What can you get out of this? Well, there's a lot you can get out of this, and that's what we're busy working on these days. But in particular, you can piggyback off of so much of all the knowledge we have about crystals, all kinds of funny crystals, anisotropic crystals, liquid crystals, many, many things, but kind of just to give you a little bit of a taste. If you have two-dimensional crystal, we know from Kostelis-Tallis, Halpern-Nelson, Young, Berezynski, that two-dimensional crystals really, as pointed out by Halpern-Nelson and Young, exhibit a melting which can be in this new universality class. It can be continuous, and it admits an intermediate phase, which is a liquid crystal-like phase, the hexatic, and it proceeds by unbinding of dislocations. You melt the crystal into a hexatic by unbinding of dislocations, and you melt the hexatic into isotropic liquid by unbinding of disclinations. And so immediately you can think about fracton insulator, where you don't want any fractons. They're just there as test charges. But then you can unbind the dipoles of these fracton matter and make a new type of a liquid, quantum liquid, which is the analog of this hexatic. It's a dipole condensate, and then you can make fracton condensate. So, you may think this is just a transcription, and to a certain extent, at a classical level, at finite temperature, it is just a transcription, but it's still something valuable. But at a quantum level, this is actually, there's now a detailed description of this. This motivates it, but now you can study this in detail within that gauge theory. Oops. It tells me to stop. But I said it 5 minutes early, so I have a couple more minutes. Um, yeah, so one thing, going in the other direction, this dual description is kind of a nice way of understanding this two-state transition. There's a Sine-Gordon-like model that allows you to describe this double-stage transition. In ordinary Sine-Gordon model, you have some gradient of some dual phase phi squared plus a cosine of that phase. And the two phases in the XY model in terms of the Sine-Gordon description are distinguished by relevance or irrelevant of that cosine. In this model, you have a Laplacian elasticity. This is what I've showed very early on in the talk. But then there are two cosines. There are cosines of phi, and there are cosines of the 90-degree rotated curl of phi, a gradient of phi. So this is dislocation. This cosine summarizes unbinding of dislocations, and this cosine summarizes unbinding of disclinations. So it's a very, much more, to my taste, much more transparent way of understanding these two transitions in terms of this dual generalized Sine-Gordon model. Well, anyway, so let me then wrap up. So, I talked about duality of these kind of exotic phases of matter in terms of something that's familiar to all of you, crystalline elasticity. And so, it gives many things for you. One, it kind of demystifies these Fracton states of matter and actually provides a physical realization of them in terms of topological defects in crystals. And, as I mentioned already, it going in the other direction gives you suggestions or motivation of how to think about new Fracton phases of matter and various transitions. For example, this Fracton condensation transition is a kind of can be described by a funny kind of a tensor superconductor. One can think about vacancies interstitials. At finite temperature, we always have since vacancy interstitials cost finite energy, at finite temperature, they're always there at some density. The higher the temperature, the higher the density, but they're always activated. But at zero temperature, you can have actually two phases. You can have a phase where there are no vacancy interstitials in the ground state, and a phase where there are vacancy interstitials in the ground state. Those are two distinct phases of matter. They both can be crystalline, but in one case, vacancy interstitials are condensed. That's a supersolid. In the other case, it's a vacuum of vacancy interstitials, so that's an ordinary crystal. So you can think about quantum melting. There's many other anisotropic crystals. There's one needs to understand, and there's some understanding of it, but not complete, of how to relate these gauge theories to these Z2, these lattice spin 1/2 models, and various other things. So let me stop with this and maybe just put up the summary in this way. Thank you for your attention.